In this video, we are going to look at linear programming. Linear programming is a commonly used algorithmic technique for solving optimization problems. So we have seen dynamic programming and greedy algorithms for solving optimization problems. And linear programming is another commonly used technique, but this time the objective function we want to optimize has to be a linear function. And also, the objective function is subject to a set of constraints, which are also in the form of linear inequalities. Okay, so that's linear programming. So first, let's look at what a linear function is. So we have n variables, x1, x2, up to xn. And a linear function is in the form of ai xi. So it is the form of a summation of ai xi for I from 1 to n. So that means it's in the form of a1 x1 plus a2 x2 plus up to an xn, where each ai is a real number and xi is a variable. And then we can also look at inequality. We can also look at equality. So let's say f is a linear function. If we make this function equal to b, then it is a equality. Likewise, we can also have linear inequalities, such as we can have f greater than b, greater than or equal to b, less than b, or less than or equal to b. And linear inequalities and linear equalities, which are to be satisfied for a given objective function, are referred to as linear constraints. So then a LP problem is to optimize an objective function subject to a set of linear constraints. And optimization could be maximization or minimization. And we also know that if we want to maximize, a function f, it is equivalent to minimize negative f. So then, in general, we would just have a standard form of maximization subject to a set of linear constraints. Okay, so let's see an example in a standard form, which is maximization with a set of linear inequalities. So look at here, we have two variables, x1 and x2. We have three inequalities as constraints. So the first constraint is 4x1 minus x2 less than or equal to 8. The second constraint is 2x1 plus x2 is less than or equal to 10. And the third is 5x1 minus 2x2 is greater than or equal to negative 2. Of course, it will be desirable to fix inequality to be all less than or equal to or all greater than or equal to, right? Just for convenience. So in this case, if you multiply a -1 at both sides, then we get -5x1 plus 2s2 is less than or equal to 2. So that way we have all less than or equal to for constraints. Okay, then we also know that dealing with inequalities is harder than dealing with equalities. So then we can turn each inequality into an equality by adding slack variables. Okay, slack variables. So for instance, we can add, so let me remove this. So we can add a slack variable x3 for this constraint and add x4 for this second constraint and add x5 for the third constraint, and all of these has to be greater than or equal to 0. So then, of course, if we add x3 here, right? So we add a new slack variable, then we can force this inequality become equality. Likewise, we add x4, and we can force this inequality become equality. And this is greater than or equal to -2. So x5 is greater than or equal to 0. So we want to subtract a positive term in order to force it become equal. So then we have the following slack form, like this. Okay, so we want to put, it's a standard to put slack variables at the left-hand side. So then, as you can see here, we have an objective function x1 plus x2, and the three constraints which were inequalities before now become equalities with new slack variables, x3, x4, and x5. Again, the advantage of dealing with equalities is that we can apply elementary linear operations at both sides of each equality, and the resulting equality is still equivalent to the original equality. So there's nothing changed for the constraints. But of course, we hope that the objective function is going to be maximized or minimized depending on what the objective is along the way while we manipulate the equalities from one form to the other. So again, manipulation on equalities using elementary linear operations, they don't change the equalities. Okay, so that means that the constraints will always be the same. And then we hope that during these operations, the objective function will get changed, and then we can get our optimal value. Okay, so in order to say things easier or to refer to things, we are going to call the variables at the left-hand side basic variables, and the variables at the right-hand side non-basic variables. Okay, so initially in a slack form, or basic variables are slack variables, and non-basic variables are the original variables in the LP problem. Okay, so these will be exchanged. Okay, so for instance, x5 could be swapped with x1, so along the way. So eventually, what we are going to have is to change these equalities, and then hopefully we can also change the look of the objective function and make it easy to find out the optimal value. Okay, so that's the idea of the algorithm, and this algorithm is called Simplex Algorithm. Okay, so before we talk about the Simplex Algorithm, we are going to look at some applications of LP, so that this will give you an idea why LP is so popular. It's commonly used technique. So for both, so this is for formulating and optimization. We can use LP to formulate a lot of optimization problems, and then we can use a simplex algorithm to find a solution, to find an optimal solution. Okay, so the first application we are looking at is to find a single pair shortest path for from S to T. So let's say you are given a directed graph, right? So directed graph, and you are given a node T, and you are given a node S and a node T. And from S to T, there may be more than one path. So what you're looking at is the shortest path from S to T in terms of the weight, the total weight on that path. So in order to formulate this problem into an LP problem, we need to first come up or define variables. So we let du, okay, be the distance from S to U. Okay, so this is a distance from S to U. Of course, for each given path, you would have that distance. So this would just be the sum of weights of each of all edges on a particular path from S to U. So then we can see here if there is, say this is U, and there is an edge from U to V, then we can see here is that dV is less than or equal to du, this would be U, this should be U, plus W U comma V, because we want the shortest one, so this is less than or equal to. And all of these du has to be greater than equal to 0. So there are the constraints. And then, so what we are looking for is dt, so which is from S to T. So then intuitively, you may think, okay, I want to minimize dt because that is the distance, I want the shortest path. So then I want to minimize it. However, if you do minimization here, then you can see that there is a trivial solution that is for all ds, for all u, ds is equal to du is equal to dt is equal to 0, because this satisfies all the constraints, and because each d has to be greater than or equal to 0, so minimizing dt, then if you get 0, it's minimal possible. So that, of course, it doesn't solve the problem. So instead, what we really want to is to maximize dt. So by maximizing it, and then and also we have this constraint that dt cannot be bigger than, right? So du plus wut. Then, of course, we know dt has to be bounded by a constraint. Dt cannot be too big, cannot be infinitely large. And then in order to find du is also bounded by from S to a predecessor of u plus a w of that predecessor to u, right? So then we can have an LP formulation for this problem. All right. Okay, so now next, let's look at a maximum flow problem. Okay, so next let's look at an LP formulation for the maximum flow problem. So in the last video, in the last several videos, we have looked at how to solve the maximum flow problem using residual networks. So of course, so now we can actually formulate this maximum flow problem into an LP problem. Then we can use a method that solves an LP to solve the maximum flow problem. So then first we need to set up some variables. So that's f. So let f sub uv be a flow from a node u to a node v if uv is an edge. Okay, so then of course each of these flows has to satisfy certain constraints. So the first constraint we know is that it has to be bounded above by its capacity C of uv. So each FUV is less than or equal to C of uv. We have the capacity constraint. And then for each u, as long as u is not the start node and the sink node, or the sink node, then what the flow that comes into u, right? So there would be several, and the flow that goes out from u has to be the same. So that is the flow. That is the flow conservation constraint. So that means that for every u that is not S or T, then the flow goes to u, that's FUV, and sum this V up is equal to the flow that goes out from u, that's FVU, for all V that going to u. Okay, so this is the flow conservation, and then of course all the flow has to be greater than or equal to 0. So that's the that's an LP formulation for maximum flow problem, and of course the objective is to maximize the flow. So this is the flow, right? As we know, this is the flow. The amount of flow that going out from S minus or subtracting the flow that going to S. Of course, this part could be 0, but this is just the flow. So we want to maximize that flow. So that is an easy formulation. So next example we're going to look at is a minimum cost flow. So in a flow problem, in addition to a capacity, so say each edge has a capacity, we are also going to add a cost AUV to each edge. So that means that if we want to ship certain amount of, let's say F is the amount you want to ship from U to V or FUV. Okay, so we have C, we have a cost A, and if you ship FUV, and then the cost is AUV times FUV. So then what we really want to do here is that suppose I want to ship D amount of D volume of stuff from S to T. And what I want is to find a way so that the total cost is minimized. Okay, so that means that the objective function is a summation of AUV times FUV. So we want to minimize it. And then the constraints are the following. First is the capacity constraint, FUV is less than or equal to CUV. And then the flow conservation constraint and the objective amount of flow, which is D, right? So you push D amount from S to T. So this is, again, this is a flow. And instead of maximizing the flow, I'm going to making the flow equal D. Okay, so that is the minimum cost flow problem, LP formulation. And the next application is a multi-commodity flow. And so in this application, let me open up a screen. So probably that's easier to explain what this problem is. So suppose we have a network, sort of like a flow network. Okay, and then you can think of this as a road network for facilities. So let's say I have a facility here, let's say S1, that produces certain parts of a big machine, and then I want to sweep this thing to T1. Okay, so using this network. So this is using some of the network. And then there's another S2 here. So there's another facilities I'm going to make, and then I'm going to shift it to T2. Right? So using the same network. And then there may be S3 here and T3, so you can shift. Right? There are other ways to do it. Now maybe there's an S4. That's T4, so you can do it. And then there may be S5, and T5 is here. And then you're going to try to shift stuff. So for each pair of SI, TI, and the shipments, the demand for the shipment is DI. And then we put this together. So we'll put this together, then we call that a commodity. So we denote this by KI. So that is a multi-commodity flow problem. So what we are interested in knowing is whether such demand can be met. In other words, whether such a flow exists. So now let's move back to our slide. Now let's look at this slide. It talks about feasible solutions and feasible regions. So once again, if we have a straight line on a two-dimensional space, right, on a two-dimensional space, let's call this AX1 plus BX2 less than or equal to C. So then let's say this is the X1 axis, and this is X2. Then anything below, well, remember X1 and X2 has to be greater than or equal to 0. So it will be in this quadrant. Okay. So the 3D area, any points in the 3D area satisfies this constraint. If you have another one here, or you have, let's say, another one, then these 3D area is the feasible region. That means any point in this, right? So in this 3D area would satisfy these four constraints. Okay, so such a geometric object is called a convex polytope, meaning for any nodes in this object, you make a line connecting them, then this whole line will either be on the boundary of the object, or they will have to be inside the boundary. And okay, so for instance, on the opposite, if you look at this, then we know this is not a convex polytope, because if you look at two nodes inside this object and you make a line, then of course the line is not inside, not the entire, there's a portion of this line which is outside the object, right? So this is a concave, so this is not a convex. So sometimes they call it concave polytope. So a simplex is a geometric object which is a convex polytope. So then we know that in order to find an optimal solution, what we need to look at is just this feasible region. So we want to find out which points will make the objective maximal or optimal. So the algorithm for solving an LP problem, we have a simplex algorithm. Okay, so and we also have, so we're going to talk about the simplex algorithm in a moment. Before we do that, we would like to mention that in addition to the simplex algorithm, which is extremely efficient in practice, but it is unfortunately exponential time in the worst case. However, I want to mention that the exponential time bound in the worst case only comes from man-made problem, from a man-constructed problem. For any natural problem, we can, so for any natural problem, that we have encountered in practice for all these years, right? So hundreds of years, and this simplex algorithm always works efficiently for those problems. In addition, but of course, the simplex is still not a polynomial time algorithm, even though in practice it is fast. So then, of course, in 1960s, maybe 68, the first polynomial time algorithm was devised, and that's called ellipsoid method. Okay, so that ellipsoid method is a polynomial time algorithm, but the degree of that polynomial is high. So in practice, it is not as good as the simplex algorithm. But then for other problems, for instance, if you want to look for an integral solution, not just a real solution, a real number solution, you want to look at an integral solution, then interior point method may be useful. So this method just walks through the interior of the simplex instead of just the vertices as the simplex algorithm would do. Okay. So the simplex algorithm will just look at each equality as a constraint. So that is the vertex, okay? Because each equality is just a line. There is no interior. There's another one. There's another one here. So they will just look at the vertex. Okay, so that's simplex algorithm. So we're going to look at this algorithm in the next few slides. Okay, so let's just go over this algorithm first, then we're going to use an example to explain how this algorithm works. So the simplex algorithm finds a basic solution from the slack form iteratively as follows. Okay, remember the slack form at the beginning, we have all the slack variables at the left-hand side, right? And then there is a linear function, slack variable, linear function, and so on. So then all of these are slack variables at the very beginning. They are basic variables. So what we do is to let all the non-basic variables, which means the variables at the right-hand side, and set them to 0. So because usually you will have a constant which doesn't have a variable. So when you set the other variables to 0, and that constant will be the value for a corresponding slack variable. Okay, and then we're going to pick, so we're going to work on a equality. So we're going to pick a non-basic variable from here, okay, from one of the constraint equalities. And then we're going to say this is the one we're going to pick. So we're going to swap these two variables so that the non-basic becomes basic, the basic becomes non-basic. And then we are going to make a new equal. So change this form to a new form. Now, is this still the same equalities? But then we are going to replace the objective function so that the form of the objective function will be changed. Hopefully, along the way, we can make the value of z as bigger and bigger. So when's it going to stop? So when it stops, that means that when all the coefficient in this objective become negative, then there is no room for maximization anymore. Then we stop. Okay, so this is the idea of simplex algorithm. Okay, so by selecting a constraint and also selecting a entering variable from the right-hand side, this process is called pivot. So we got to do this until, so each time we gotta do this until the coefficient, all the coefficients in the objective function have become negative. And then we are done. So then later we're going to show the result, the solutions we found in this process is maximized. So for that, we need to look at an LP dual. So this LP dual. Okay, for now, we are going to just look at this simplex algorithm, familiar ourselves of what this algorithm is about. So the best way to do so is to use an example. The best way to explain the simplex algorithm is to use an example. So given here is an example of 3 variables. We have the objective function 3x1 plus x2 plus 2x3. We have 3 constraints. So now we're going to introduce for each constraint a slack variable. So we're going to call it x4, x5, x6. We're going to put it on the left-hand side. We're going to make each of these constraints to force them become equality. So then x4 in this case is equal to 30 minus x1 minus x2 minus 3x3. So that's what it is. And the second one will be this, x5 is equal to 24 minus 2x1 minus 2x1, 2x2 minus 5x3. Likewise, x6 is equal to 36 minus 4x1 minus x2 minus 2x3. So all of these slack variables are also greater than or equal to 0. And what we want to maximize is an objective function z. So let's call this z. So then the pivot procedure is to first let all the non-basic variables be 0. So if you let s1, x2, x3 be 0, then you get x4, which is equal to 30, x5, 24, x6, 36. So then we want to select an equality. Maybe we want to select this equality because x6 is larger using a greedy kind of thinking. And then we pick a pivot elements. So for instance, we just pick x1. Because you can also pick x2, you can also pick x3. So let's just say that we pick x1. And then in this case, then we have x1 becomes 9 minus x2 over 4 minus 2x3 over 4 minus x6 over 4. Okay, so we can do that calculation here. So this is what we pick. x1 is the entering variable, so we're going to move to the left-hand side. So we got 4x1, and then the right-hand side comes 36 minus x2 minus 2x3 minus x6. So then you move this 4 over to the right-hand side, and we got x1, which is 36 over 4, which is 9, minus x2 over 4, minus 2 over 4, so that's x2 over 2, and then minus x6 over 4. Okay, so that is this thing here. Okay, and then we are going to replace x1 in the objective. Remember, the objective is 3x1 plus x2 plus 2x3. Okay, so So we can just put it here. So originally the objective is z, which is 3x1 plus x2 plus x3. So this x1 is now here. So then 3 times 9 is 27. And 3 times negative x2 over 4 plus x2, then it becomes x2 over 4. And then 3 times this. Okay, so actually is x3 over 2. So 3 times that plus x3 is equal to x3 over 2. So you got x3 over 2. And then x6 is from x1. So you just put it in there. So 3 times that becomes 3x6 over 4. So that the objective becomes this. So as you can see here, if you let x2, x3, x6 be 0, then you get a value of x1, that is 9. Okay, and so you obviously you also get x4 is 21, x5 is 6, and then you get, at least now I know 27 is a feasible, is a solution that may not be the maximum solution, but now I know 27 is a solution. So then we're going to repeat this until all the coefficients of the variable in the objective becomes negative. So we have 2 positive ones. So then, of course, we can pick, let's say we pick S2 as a leaving, as an entering variable, and then we're going to pick an objective. We're going to pick a constraint. So X2 is we're going to pick. The value of x1 is already determined. We're going to say, okay, which one we're going to do? Maybe we can either pick x2 or we can x3. And this looks kind of, so this is easier. Maybe this one is easier to work with. So we're going to pick x3 and move to the left and move x5 to the right. So that's what we do here. And then after some manipulation, then this is a new constraint x3, which is 3 over 2 minus this plus that, and so on. So then we're going to replace z. So z now has this new value. So likewise, you got to change all this x1, x3, and x4. So these are equalities, okay? So they are still the same equality as before, but the variable on the left-hand side are different. So then you can, as you can see here, you have still one positive coefficient. You let x5, x6, and x2 be 0, you get z, which is 1, 1, 1 over 4, which is greater than 27 earlier. And so since you still have this x2, so we are going to pick a x2 as an entering variable. So you can either do it from here or from here. Okay, if you do it from here, then you move x2 to the left and x4 to x3 to the right. So what we have is now x2 becomes 4 minus 8x3 minus 2x5, 3, and so on. So then z becomes 28 minus x3 over 6 minus x5 over 6 minus 2x6 over 3. So all the coefficients now become negative. So that means we can stop because there is no more room for increasing the value of z. So what we are going to let what I'm going to set is x3, x5, and x6, 0. So this is x1 is the original variable, so I want to set 0. And then x4, x5, x6, I want to set 5, 0, 6, 0. Okay, so what we're going to get here is x1, which is equal to 8 when these are set to 0. S2 is equal to 4 when it's set to 0. And x4 is 18. But these are slack variables, we don't really care. So this is a solution. It is not, oops, sorry, including 0. So this is a solution for x1, x2, x3. It is not only feasible, it is also maximal. So in this case, the maximum value is 28. As I said, we're going to use LP dual to show that the simplex algorithm returns the maximum solution. Okay. All right. So maybe we'll stop here for this video. We're going to continue to look at simplex algorithms next time in the next video.